Hello everyone. In this and the next video, we'll be looking at another ensembling method called boosting. In this video, we'll look at boosting for regression, and then in the next video, we'll be looking at boosting for classification. So boosting was really developed to answer the question, what if I have a whole bunch of weak models that's just slightly better than a random guess? Can I combine them into a much stronger combined model? Boosting is a little bit different from some of the other ensembling methods that we looked at. In bagging, for instance, what you do is you take your data set and you grab bootstrap samples from your data set and then fit a separate model on each of the bootstrap samples. And then you simply average all of the different models. But one model doesn't really know anything about another model. In boosting, the strategy is a little bit different. You start by first training one model, and then you check what types of errors does this model make. And then you use that information when you're training the next model. And then you go through the steps like this. Each model can basically check, what did the models before me, what did they mess up on? What were the training points that they struggled with? And then this current model kind of focuses on the mistakes that the previous models made. So in this video, we will be looking at boosting for regression. And this is actually an algorithm for training a boosted regression model. And what I will first do is just give a high-level introduction of the algorithm and then step through an example, which will hopefully make everything clear. So I've broken the algorithm down into 3 steps. The first step is an initialization step, where we just set some initial values. The second step is, so I've broken down the algorithm into 3 steps. In the first step, we just initialize the whole process. In the second step, we're going to iterate. We start with a little b is equal to 1 up to big B. And in each of these iterations, we're going to train a new model, f little b with its own set of parameters, theta little b. So we're going to train, in the end, capital B different models. And then in the third step, that's where we get out our final model, the thing we're going to use. We simply combine the capital B models that we trained in the iterations. The models are combined by simply adding up their scaled predictions. And hopefully these steps will make sense when we go through the example. Let me just quickly talk about what happens in the first iteration and then what happens from that point onwards. So, like in any machine learning setting, we use some data to train the model. Okay, so we've got some data. We've got input vectors. For example, we've got x1, that would be our first input vector. And going with that first input vector, we of course have our target, y1. We're doing regression, so that would be some continuous value that we're trying to predict. We've of course also got our second training item up to our nth training vector. And going with x2, we've got y2, and so on. So sometimes we combine all the input vectors into one matrix called the design matrix X. We do that by taking the transpose of each of the training vectors, that turns them from column vectors into row vectors, and we stack all of them into in this one design matrix called X. We do something similar with the y values. We stack them all into one vector, the y, the target vector. Okay, so in the first iteration, so when b is equal to 1, when we're in that iteration, we are simply fitting a model with inputs x and outputs y. And then what we do is we check what are the mistakes that the resulting model makes in predicting the y's. And we combine all of those mistakes into one vector, which we call the residual vector r. Okay, and the residual vector r, the first item will be the mistake we make on the first input-output pair. The second value will be the second residual, and so on up to the nth residual. So basically each of the elements in here tells us, when we train this model, how wrong are we getting the first prediction, the second prediction, and so on. Okay, and when b is greater than 1, in other words, every iteration after the first iteration, instead of fitting a model on the inputs x and the outputs y, we are going to have inputs x and outputs r. Okay, so we're in each iteration, we're going to fit a model to the residuals, how much we got wrong. So I'm not sure that makes complete sense, so let's just look at an example and then hopefully everything comes together. Okay, so in this example, it's just a one-dimensional regression task. So we've got one input feature x and one output variable y that we're trying to predict. And what we're going to do is we're going to combine a whole bunch of weak models and try and do regression on this data set. So we need to decide what's basically going to be our small building block. What's the basic model going to be? So in this example, what I'm going to do is I'm going to use as our weak learner, as our kind of basic building block model, I'm going to use a very, very simple decision tree. Okay, in fact, it's a decision tree with just a single node, okay, that can make a single split. And this is sometimes called a decision tree stub. It's basically a decision tree with only one split. Now, this is a very weak model, right? It's basically the next best thing to simply predicting the average value for all inputs, right? So the dumbest thing you could do in this regression problem is basically calculate the average, and for any of all of these data points, and for any input, just predict the average. This is just slightly better than that, because what we're going to do is we're going to do one split somewhere in this space, I don't know, somewhere here, and then in the one region we're going to predict the average, and then in the other region we're going to predict the average as well. You can use any base model for boosting, but decision tree stubs are actually used quite often in practice. So now let's step through the algorithm kind of systematically. So we start by initializing our residuals by simply setting each of the residuals for all of the training points. We're setting each residual equal to the target value that we want to predict, okay, for all n training items. And then we set f x theta. This is our final model. We're just setting that equal to 0. Okay, and you will see how we basically systematically improve our final model as we go through the different iterations. Next step, we go for iteration b is equal to 1 up to b. Okay, so let's say we're just in b is equal to 1. We're just in that first iteration. When we're in that iteration, because of the way that we initialized here, we actually have that our residual vector is just equal to our target vector. Okay, so then when you're in this step 2a here, which says fit model f1 x theta 1 to input x, outputs r, but that's really saying outputs y. Okay, so in the first iteration, we're simply fitting a model to our input output data. Okay, so let's see what that model does. Remember, I'm fitting this kind of very, very small, sad decision tree stub, and I'm fitting it to this data. So let's just do that. So this shows the prediction from that model. We're in the first iteration, b is equal to 1, and this plot is showing the output from our first model, f1 x theta 1. Okay, and the dashed line here, that shows the prediction from this model. So the decision tree decided to split at just a little bit more than 3. Okay, and in this region, in this first region, it's simply predicting the average value of all of the training points in that region. And in this region, it's simply predicting again all of the average value of all of the training points in that region. So this is the prediction of F1. Okay. Now, in the next step, what will we do? In the next step, what we'll do is we will update the model, okay, by adding a strong conversion. What does this mean? We're going to update the final model, fx, okay, by adding this current model, f1, okay. We're going to add a strong conversion by some parameter lambda, which is smaller than 1 and greater than 0. We're going to add a strong conversion of this f1. We're going to add that to our final model. So what does this look like? We started with a final model that's just set to 0, and now we're simply adding a strong conversion of f1. After completing the step B in the first iteration, this is the output of our model. Okay, our model is simply lambda, which is some parameter that you can choose, x theta 1. Okay, some scaling parameter. Okay, so if we go, let's just go back to the previous slide. We simply took this prediction and we just scaled it. And that's what's giving us this prediction in step B. Now we go on to the next step. So we're still B equal to 1, and now we're at step C here. Okay, and this step says update the residuals. Rn becomes the previous Rn minus lambda f1 xn theta 1. Okay, so at b equal to 1, when we're in the first iteration, remember that all the r's are basically the y's from the way that we initialized. So this means that Rn will now become yn minus lambda f1 xn theta 1. What does that mean? Let's say that this point here, this blue point here, let's say that that's y5. Okay, this is y5. Okay, and that's the 5th training item, and that's the target value, and the input value is just more than 2. Okay, for that training point, our prediction is where? There. Okay, so that point there, that's just lambda f1 x5 theta 1. We trained our first model, and that's the value, and the scaled version of that model is predicting. Now, what is the mistake we're making? The mistake is basically this height here, okay? And that's called R5. That's the residual, okay, the 5th residual. So what happens in this step is we're basically checking what is the mistake that the model that I trained in this iteration, what is the mistake that I'm making in this specific iteration. Okay, perfect. So we update all our residuals, and then we're done with the first iteration. Okay, so what we will do next is we will go back and we will go on to b is equal to 2. Now we're in this new iteration, b is equal to 2. We've updated our residuals, and then we just continue with the algorithm. So step A says fit a model b, which is now f2, to inputs x and outputs r. Okay, and r is now just the residuals from the last slide. So what I've done here on this plot here, I've got again my inputs x, but instead of having y on this axis here, I've instead plotted the values of r, the different values of the mistakes that I made. So let's just look at the 4th training item there, that 4th item. You can see that the residual for that item is just around, I don't know, just more than 0.3 or something like that. And if you go back, let's just go back to the previous slide. 1, 2, 3, 4. This distance here will be that value that's just more than 0.3. So that height there, that is the distance from 0 to that height there. Okay. And what we're doing now in the second iteration is we're fitting a second model, f2, okay, which has some inputs x. some parameters theta. And what we're doing is we've got all these different residual points here. We fit, again, a decision tree stub, just this very small decision tree. We fit that to the residuals. So we're not training on X, Y's, we're training on X residuals. Okay, and we train a model to basically fit the mistakes that the first model made. Okay, that's what we're doing. So in the second iteration, we're training a model to basically match the mistakes that the first model made. So we train that model, and this is the prediction from that model. This dashed line, that's the prediction from F2. Okay, so we're in the second iteration, we're in step A, we fit the model, we get that prediction. Now we go on to the next step, step B within our iterations. So we're still in the second iteration, and we're now at step B. What does step B say? It says, take the previous model, the previous final model that we had, and add the current model times the scalar parameter. Okay, so this means that at this point in our algorithm, our model consists actually of two models. It consists of lambda times F2, our second model that we trained, plus lambda times F1, the first model that we trained. So this plot here actually shows the output if I take the scaled version of F2 plus the scaled version of F1, then I get this prediction here. Now let's compare that to the output that we got just a few slides ago when we just had the scaled version of F1. What did the output look like then? How well did we fit our training data just a few slides ago? So this is the scaled version of our first model, and what I will show now is when we add the scaled version of that second model, which was fit on the residuals. The result looks like this. So adding one model, we get this little step thingy in the middle of our plot. Okay, that's it. So now we're done with the second iteration, step B, and we will now go on to the last step, C, which says update the residuals. So now what you do again, you check what are the mistakes that F2 is making, the scaled version of F2 is making, and update the residuals, basically update my mistakes. How big is the mistakes that I'm making on all of my training data points? Okay, and then when I'm done with step C, then I go back out and I repeat again. So now I'm in B equal to 3. We again fit a model F3 to X with the residuals from the previous iteration. And then what we do is we add a scaled version of that model to our final model F. And then this is the result that we're getting. Here we've got X and the variable Y, the variable I'm interested in predicting. And what I'm plotting here is the result of the scaled version of F3 plus the scaled version of F2 plus the scaled version of F1. And what you can see here is we're getting another little bit of a step. So let's quickly just jump from the first iteration to the second to the third. So this is iteration 1, this is iteration 2, and then this is the third iteration. And you see what's happening, right? I'm basically every time fitting a model to fix the mistakes from the previous model. And in that way, I'm systematically getting better at matching the training data. This is what happens at iteration 4. And what I will do now is just quickly jump ahead a whole bunch of iterations. So this is the prediction at iteration 15. Okay, and if capital B is equal to 15, okay, then this might be our final model and we've reached the end of our boosting algorithm. And what you can see here is that you have a pretty nice fit to the training data. You should remember that basically this is a combination of just 15 very, very silly models, right? What we did was we just trained 15 decision trees, which only has one split, and we're combining them in this way. So basically we're adding up the 15 little decision tree stubs here, and we're getting this output. One question you might have at this point is, how do we actually choose this value of lambda, the scaling parameter that we use here? Lambda is a hyperparameter, so that means we need to choose it before we kick off the algorithm. And we can do that using a validation set. So we can try out a few different values of lambda, because lambda might also depend on the problem. Values might range between 0.01 or go as small as 0.001. And one thing to notice, just if you have a very small lambda, then it might require a large number of models. So your B might be very large in order to get a good fit. So boosting proves to be a very effective way of combining a whole bunch of much simpler models. In this video, we looked at boosting for regression, and in the next video, we will now look at boosting for classification.